Welcome to STEM Pod Leaders, Conversations with Today's Great Minds. My name is Nathan Goldrich, the founder of the STEM Pod Tutoring Academic Outreach Program. I am here with co-host Eric Rabin, a medical student at the Feinberg School of Medicine. Our guest was born in Logan, Utah in 1940. He obtained his bachelor's in physics from Caltech in 1962 and earned his PhD in physics from Princeton in 1965. After spending a couple years more at Princeton as a postdoctoral fellow, he returned to Caltech to become a professor. His work for decisive contributions to the LIGO detector and the observation of gravitational waves brought him the 2017 Nobel Prize in Physics. Aside from his work on LIGO, he worked as executive producer and science advisor on the movie Interstellar. For more information, check out his book, The Science of Interstellar. We are psyched to have Dr. Kip Thorne on the program. Thank you so much for being here, Dr. Thorne.
It's a great pleasure to be with you. I admire what you're doing. Let me see what I can do to help out.
So what do people mean when they say that the universe is warped?
What we mean is that the shape of space is not like a flat sheet of paper. For example, if you look at a very dense star, we call it a neutron star, that has a diameter that may be 30 kilometers, then you would expect that the circumference would be pi times that diameter, or roughly 100 kilometers. But in fact, the circumference is far less than that. The circumference, instead of being 100 kilometers, might be 70 kilometers or 60 kilometers. So it doesn't obey the laws of geometry, which say that diameters times pi is equal to circumference. It's different from that. And that is the kind of difference you would get if you had a soup bowl and you computed the diameter and the circumference, the diameter being measured along the porcelain or the glass of the bowl. The diameter is generally bigger than it ought to be, given what the circumference is.
And how does black holes relate to this?
Yeah, okay, so the key thing about black holes is black holes are made from warped space, and we also deal with warped time. Time near the surface of the Earth flows more slowly than time at high altitudes, more slowly by about 1 second in a century. So that's not much slowing of time, but it is slower here. And so what about black holes? Well, black holes are things that are not made of matter like you and I. They're made entirely from warped space and warped time. So for a black hole, the diameter is enormous compared to its circumference. And for a black hole, time slows to a halt. It just stops flowing at the surface of the black hole, or the horizon, as we call the surface of the black hole. And so these are features of the black hole. They also are what the black hole is made from. It is made just entirely out of this warped space and warped time.
And why does time slow as you approach the horizon of the black hole?
So there's an intimate connection between the rate of flow of time and gravity. Einstein found this connection back in 1912, before he had his full theory of gravity, which is called general relativity. But already in 1912, he understood this. Qualitatively, I like to describe it as this, in this way, that things like to be where they will age the most slowly, and gravity pulls them there. So time flows more slowly on the surface of the Earth, as I said before, slightly more slowly than it does at high altitude. And so gravity pulls things to that location. That's a fundamental feature of the laws of nature. You might continue to ask why, and at some point you get to the point where all I can say is that's the way nature works, and we know that that's the way that nature works, both from a very, very beautiful laws of physics that Einstein discovered that are so beautiful that Einstein took the attitude, how can they possibly be wrong when they're so beautiful? But you know it also, more importantly, from observation, and have very high precision observations that show this slowing of time near the surface of the Earth compared to way up high. The very precise relationship between the amount of slowing of time and the strength of gravity, that precise relationship which Einstein gave to us, his laws, that has been measured to this extremely high precision.
Does that mean that time theoretically stops at the singularity?
It theoretically stops at the horizon. If you're hovering at the horizon and somehow avoiding falling in. If you fall through the horizon into the interior of the black hole, time does not stop for you. It seems pretty normal to you. But in fact, it turns out inside the black hole, time is flowing in a direction that you would have thought was a space direction. It's flowing toward the singularity at the center of the black hole. But you feel time as being perfectly normal. However, because you cannot turn around and move backward in time, you can only move forward in time, you are dragged by the downward flow of time, dragged into the singularity. You're inside the black hole.
So is there a closest location you can get to the singularity of the black hole while you're still able to theoretically escape?
The closest you can get is the horizon, the place where time starts to flow downward. And so the horizon is the surface of the black hole in that sense. If you get inside the horizon, there's no escaping.
Given that a black hole can have a mass of up to 3 times that of the sun, but only have a diameter of 10 kilometers, are black holes constantly morphing into different shapes that are more entropically favorable?
Black holes, when they're quiescent, once they've settled down, they have, if they are not spinning, they're precisely spherical. And if they're spinning, then they're a little bit flattened, like the Earth is flattened by centrifugal forces pushing its equator out relative to its poles, but it's not a lot of flattening. And when a black hole is disturbed from this, it very, very quickly settles back down into this unique shape. So it's not constantly morphing. The black holes, when they're born, they may be very distorted, but extremely quickly they settle down. By emitting gravitational waves, they settle down into a spherical shape if they're not spinning, slightly flattened if they are spinning.
Much of your work has been about black holes and measuring gravitational waves. Given the enormous size of the universe, how rare is it for two black holes to collide?
So two black holes will collide in our Milky Way galaxy about once every 100,000 or 1 million years. So that's not very often. But on the other hand, there are billions and billions of galaxies in the universe. And so this is happening every few minutes in the universe. There are black holes colliding. So my colleagues in this LIGO project have built gravitational wave detectors that see out through a large fraction of the universe. And so they see black hole collisions now when they're all generally up and observing several times a week. And it will get up in the future to many times a day. But that's because you're looking out through a huge portion of the universe.
What can gravitational waves tell us about the universe?
Let me go back and talk about electromagnetic waves. Electromagnetic waves, which are much more familiar, they are made from oscillating electric forces and magnetic forces. And they include light, radio waves, X-rays, all the familiar kinds of radiation that we normally deal with. They're electromagnetic. And they are produced by oscillating electric charges or currents, like the currents in a radio transmitting antenna that are oscillating in that emitting antenna. Gravitational waves are produced by the motion of mass, large amounts of mass or energy oscillating. And so if you have colliding black holes, these black holes are not made from matter, so they don't have electric charges, so they cannot emit electromagnetic waves. They can't emit light or radio waves. But because they have huge amounts of mass and energy, these colliding black holes emit gravitational waves. So gravitational waves are the ideal tool for observing things like black holes that have huge mass and energy, don't necessarily, and in this case, absolutely don't have any electric charge. So they observe a very different aspects of the universe than electromagnetic waves.
What happened when the gravitational waves produced by the black holes hit Earth, and how were you able to detect them with LIGO?
So these gravitational waves, let me go back again first to electromagnetic waves. What do? Since they consist of oscillating electric fields, they grab hold of electric charges, electrons or protons, and wiggle them back and forth. And so it's an acceleration back and forth in a direction perpendicular to the direction the waves are traveling. So if the waves are coming in from the sun and the sun is overhead, then these electromagnetic waves, light, for example, will wiggle an electric charge like an electron back and forth horizontally. Gravitational waves, instead of pushing stuff back and forth, they stretch and squeeze it. So if the source is at the sun and the sun is overhead, these waves are traveling down from overhead. They will take you and stretch and squeeze you in a horizontal direction. You may be stretched in the north-south direction and squeezed in the east-west direction. And then a moment later, that will reverse. So you're squeezed north-south and stretched east-west. The amount of stretching and squeezing is exceedingly small, so small that you don't notice it. For the gravitational waves that LIGO has seen, this squeezing and stretching and squeezing is, one way to say it is technical language, it's a part in 10 to the 21. If it will take you and it will squeeze you, change your thickness from north to south by 1 part in 10 to the 21. And that's an extremely small amount. In our case of LIGO gravitational wave detectors, then we actually measure the stretching and squeezing by having mirrors that hang from overhead supports. These are heavy mirrors. They weigh 40 kilograms, about 100 pounds, and they are separated by 4 kilometers, about 2.5 miles. They're pushed back and forth relative to each other by the gravitational waves by an amount that is about 1/100th the diameter of the nucleus of an atom. When you think that the nucleus of an atom is 100,000 times smaller than the atom itself, that means that pushing back and forth is about 1 part in 10 million of the size of an atom. Extremely small amount of stretching and squeezing, but the superb experimental team of experimental physicists that I work with has succeeded in building detectors that can measure those tiny stretchings and squeezings.
I wanted to read to you some data about the first gravitational wave that you detected. The two initial black holes had 29 times and 36 times the mass of the sun. Their collision produced the energy associated with 3 times the mass of the sun. The power output within 1/10 of a second was 50 times larger than the power output from all of the stars in the universe combined. What does that mean to you? That to me sounds so amazing.
It sounds so amazing to me too. It really was a shock when I went in and did the numbers on how much power it was. We sorted these numbers out before we made the announcement of the gravitational wave detection. I was quite surprised it was that big. I knew it was big, but of course it's that power for 1/10 of a second. And so the total energy, which is the amount of power times how long that power lasts, the total energy was the energy you would get by completely annihilating 3 suns and turning it into gravitational waves. So that's that's a lot of energy, but it's not a lot on cosmic scales. But because it comes so fast, so extremely fast, the power is higher than the power output of anything else that ever occurs in the universe, as far as we know, except the birth of the universe itself, the Big Bang explosion in which the universe was born. So amazing that what the first thing we saw was something with more power output than anything that occurs in the universe except the universe's birth.
You've had more gravitational waves detected since then. Are you consistently seeing or being shocked by these numbers that you do see?
Not shocked at all. These are basically what I had expected. Uh, and the first signals were a little stronger than I expected, but not a lot stronger. And so things have gone more or less the way that I expected, going way back to the 1980s when we were just in the process of formally proposing to build these instruments. We knew enough about the universe to have some sense as to how many colliding black holes there were out there. And it's just an issue that we searched for a few months and then we shut the detectors down for a year or so. And then we searched for a while, then we shut down. When we shut down, then we improve, the experimental team improves the detector so they can see a little farther. And if the detectors are improved so they see 2 times farther, then you're seeing an amount of the portion of the universe whose volume is 8 times bigger. You know, it's 2 times farther in all directions, and there are 3 directions: up, down, east, west, north, south. So it's 2 cubed is a factor of 8. So just a doubling in how far you can see, you see 8 times more frequent black hole collisions because you're seeing 8 times more volume of the universe. And so these collisions are going up. We have now seen 64 black hole collisions, but the instruments are shut off to be improved most of the time. And you gain a lot more by shutting down for a year and then observing for a few months than you would by just observing for a whole year.
What kind of improvements do you make to the machinery?
Well, at this stage, it's primarily cleaning the machinery up, though not entirely. The, the, these instruments are extremely complicated because there's so many things that can go wrong. If you're trying to measure these exquisitely small motions, the rain falls on the ground outside, that causes the round to vibrate a little bit. Those vibrations create little vibrating gravitational forces that because the ground is moving up and down, the gravity it produces is changing very slightly. Those little vibrating gravitational forces, they influence our instruments. That's what we call gravitational noise, Newtonian gravitational noise. Even that becomes a problem. Much worse if you don't compensate for it is just the vibrations of the earth. Then they vibrate the overhead support from which the mirrors hang, and that causes the mirrors to vibrate. And you have to guarantee that those vibrations are smaller than the motions induced by a gravitational wave, which means you have to have a superb suspension system, like in a very expensive, fancy automobile, but a lot better than that. And so many things can go wrong. These instruments are tremendously complicated, and that means that in terms of that, when we first turned on and saw these gravitational waves, we had instruments that were about 3 times worse than they were designed to be. So what's been going on in the last several years then is just cleaning them up and getting down toward our design sensitivity, as we call it. But it turned out that there was one problem that was worse than we expected, and that was that we had to operate with very high laser power. We're using light to measure the motion of these mirrors, and we have to operate with enormous power in the light that's bouncing back and forth between mirrors. And there were technical problems that causes the mirrors to heat up and they deform. It causes triggers through some complicated processes, vibrations in the mirrors that cause the shape of the laser beam to be distorted. And a lot of problems of this sort meant we had to go in and make a real change in the design of the instruments. It was a change that we were planning to make some years in the future. But we made a change by injecting into our instruments something called the squeezed vacuum, which is a whole story in quantum theory separately. But basically, injecting a piece of technology that is really futuristic technology in order to deal with that. And so we're making occasional major changes, but mostly just cleaning up the instruments.
You've done a great deal of work on wormholes. How are wormholes different from black holes?
So a wormhole is a hypothetical object that is predicted by Einstein's general relativity, just like black holes are. It's a hypothetical object that connects two different regions of space, and that makes that connection by going through a higher dimension. In the movie Interstellar, the physicist Romilly takes a sheet of paper and he explains this to Matthew McConaughey, who's playing Cooper. Takes a sheet of paper, he bends a sheet of paper around, and he says, I want to travel from one end of this sheet of paper to the other sheet. He bends the sheet of paper around so the two ends are close together in that higher dimension. And then he shoves a pencil through the two pieces of paper at the two ends of the bent paper and says that's a wormhole. It takes you from one end of the paper to the other. That's basically what a wormhole is. It's a lovely graphical example. It's a connection between me in California and somebody in New York City that makes the distance that you might travel be a few meters instead of thousands of kilometers. And so these are hypothetical things that are like black holes are made from warped space. But the issue then, having seen that these things can exist according to general relativity, the issue is whether they really do exist. Well, first of all, all the laws of physics allow these wormholes to exist? Because general relativity is not the only law of physics. Do all the laws of physics allow them to exist? If all the laws do allow them, then do they occur naturally in the universe? If they can't occur naturally, is it possible for a very advanced civilization to build them? Because these things would be wonderful for interstellar travel.
If you were to somehow traverse through a wormhole, what would you observe and how long would it take until you made it to the other side?
Well, how long it takes until you make it for the other side depends on how long the wormhole is and how fast you travel. But you could imagine wormholes where you go through rather quickly in a matter of minutes or seconds to travel from California to New York. We certainly don't have any wormholes today that would allow us to do that. My best guess is that we never will have them. But it is just a question of the shape and size of the wormhole and how fast you travel.
How is time affected by wormholes?
So that depends on the properties of the wormholes. And so maybe I should back up and tell you the history of our understanding of wormholes. John Wheeler, who was my PhD advisor and my mentor at Princeton University way back in the early 1960s, in the 1950s, he thought that wormholes were very likely to exist in the universe and be very important. He thought that black holes would not exist, that they were too bizarre and that nature would not allow black holes. It turns out black holes do exist. He was quite wrong. And wormholes probably do not, but we just don't know that. So what he discovered to his dismay in his own research about the time that I was his student was that if you have a wormhole and you don't have any kind of matter inside it to affect it, the wormhole will pinch off so quickly that nothing can travel through it. It will shrink right down and destroy anything that tries to travel through. And that was a big shock, a big surprise. And then the other surprise for him was that, in fact, black holes turned out to be things that are extremely robust. And once you form them, it's essentially impossible to destroy them. And so things were totally upended in the period that I was his student, basically. And then it was much later that I and others in the late 1980s began to ask the question, would it be possible to prevent wormholes from shrinking and collapsing by putting some sort of matter or fields inside them. And we found out, perhaps not surprisingly, that the only way to hold a wormhole open is to put something inside the wormhole that repels gravitationally. So it pushes the walls of the wormhole apart, holding them open. And to repel gravitationally, it has to be something that's made from negative energy. And the intriguing thing was that we know how to make matter that has negative energy and correspondingly negative mass, because Einstein tells us that mass and energy are equivalent. We know how to make tiny, tiny amounts of this thanks to the laws of quantum physics. And this is done in the laboratory. And so then the question became, is it possible the laws of nature allow you to make and collect together enough negative mass, negative energy inside a wormhole to hold it open? And that has been a major area of theoretical research. We don't have the technology to do this experimentally, but a major area of theoretical research asking what the laws of physics, all the laws of physics say about that. The key thing is that quantum physics is the set of laws that govern whether or not you can have material of some sort that has negative mass or negative energy. And these laws of quantum physics seem to be saying that it's impossible to get and collect together enough negative mass or negative energy to hold a wormhole open. But we don't know that for sure. There's a very nice little book, oh boy, I can never remember, by Alan Everett and Thomas Roman. If you just look them up the internet, it's called something like Space Warps and Time Warps. I've forgotten the title. Anyway, look up Alan Everett and Thomas Roman. That goes into this in considerable detail and explains where we stand with regard to learning whether you can have enough negative mass material to hold a wormhole open. Okay, so that's sort of the story of where wormholes stand. The issue of how they influence time, it depends on the properties of the wormholes, which depends on the details of the negative mass that you've put in there to hold the wormhole open. So we know that if you're going to be able to travel through the wormhole, then it may be able to slow time a lot, but unlike a black hole, it cannot have a horizon where time is flowing downward when you reach the horizon, because you'd never be able to travel back up through that horizon. Wormhole, by definition, is something that you should be able to travel back and forth through in either direction. How much influence has on time depends on details. That depends on how it was built and how much negative energy or negative mass you have when you build it. And so I don't have a clear, distinct answer in that case, by contrast with black holes.
Switching gears to Interstellar, what prompted you to bring science to cinema?
I never had any aspirations to be involved in movies, but I do live in Pasadena, California, not far from Hollywood. And I was single for about 10 years between the mid-70s and the mid-80s. And I did date a lot in Hollywood. So I had a girlfriend who was at the beginning of her career to make movies, her first movie, and she was sort of the initiator of it. It was a movie called Flashdance, which was quite successful way back around 1980 or so. And she was the producer of Carl Sagan's movie Contact. And so we dated for a while. The romance never went anywhere, but we became good friends. And it was her phoning me up one day in 2004 saying, how would you like to brainstorm with me for a movie? And I said, sure, that sounds fun. But I also did realize immediately, maybe if I did this, we could make a movie that could have an impact in terms of inspiring people about science. And so that's what it turned out to be for both of us, both an enjoyable process and making a film that could be inspirational about science.
When you work with Christopher Nolan, one of our favorite directors of all time, how are you able to communicate the highly complicated science with him? Were there any notable research papers that you recommended?
So I began working initially with Christopher's brother, Jonathan, or Jonah, as we call him, Jonah Nolan. Jonah wrote the first three drafts of the screenplay. And for Jonah, I pointed him to a large amount of stuff, of semi-popular, semi-technical books about topics ranging from relativity and gravity to astrobiology uh, and and astrophysics more broadly, planetary science. And he uh, read these things voraciously before he started writing on the screenplay. His brother, Chris, is very different. Chris has a rather good understanding of science, I think, himself, and good intuition about science, based largely on browsing the web, which I guess is a modern way to self-educate. Just along similar lines, our original director on in the early phases on Interstellar was actually Steven Spielberg, and then Steven left the project and Chris came on to direct, and Chris changed the movie enormously. But Spielberg doesn't know much science at all, but his father knows huge amounts of science. His father is now, I think, 101 years old, Arnold. But Arnold learned his science from reading science columns in science fiction magazines from the 1930s and 40s. You don't learn it at the level of being able to do serious scientific research that way, but you can get a real understanding phenomenologically of what goes on in the universe.
When making Interstellar, you required that nothing should violate established laws. What science that you communicated through the movie are you proudest of?
Well, I think just generally overall, the movie as a whole, this was an opportunity to really display science in some of its richest forms and a wide variety of science, as I describe in my book, The Science of Interstellar. What I'm really proud of is the whole panoply of things that underlie science, that underlie that movie. The venue of the movie is warp space-time, and so it does involve black holes, it involves wormholes, and it involves a little bit of sending information backward in time through a higher dimension, and it involves gravitational slingshots, just a wide range of things that are aspects of warp space-time. I'm just really pleased that we were able to make a movie where you see these things in action. You don't necessarily understand what you're seeing unless you go read the Science of Interstellar. You see them in action, you get some sense that the universe is more rich and more interesting than you might ever have imagined before you went to see the movie.
Aside from Interstellar, uh, especially when I was watching SpaceX, and some of the visuals that we saw on the news reminded me a lot of 2001: A Space Odyssey, which was a huge movie that came out in 1968 and changed science fiction forever. Many people call it the greatest science fiction movie ever made. But I've always been curious how grounded that movie is in the science.
Well, I thought it was very well grounded, aside from the final piece, which was a fantasy, where you see the guy going out through wild visuals and winding up in a room and aging very quickly from baby, or is it the other way, to ancient man. I mean, the very end of it was really weird. But let me say, with regard to that, with regard to the ending, uh, in one of my first meetings with Christopher Nolan on Interstellar, he said, "I've always admired Stanley Kubrick's ending in 2001. He said, I want to make an ending that is equally mysterious, uh, and uh, and I want you to help me do that." And so I don't know whether the one in Interstellar is equally as mysterious or not, but I think it's quite interesting that Chris was so inspired by the ending of 2001. But setting aside the ending of 2001, it was extremely well based in real science, and that was because Kubrick was working with Arthur C. Clarke, who was a physicist and really understood physics very, very well.
So going back to the beginning, growing up, what inspired you to go into the sciences?
Well, I had the huge advantage over other people who may want to go into science that I grew up in a family where my father himself was a scientist. He was a soil chemist. He specialized in arid land agriculture, the soils, fertilizers, and so forth for making agriculture in places like Utah, where I lived, or in the Middle East, in Iraq, Iran, or Pakistan, making it much more effective. So I grew up with science in the family. My mother was also an academic. She was an economist, but she inspired me in the sense that she took me to a lecture about astronomy when I was 8 years old, about the solar system. And I became very excited about the ideas of the sun and the planets, the enormous distances between the planets, like in terms of their sizes. We did projects together to get me started. Then I started reading on my own. She encouraged me to follow my nose. So with that kind of background, it just came very naturally to move towards science for me. And that's very different from most of my colleagues, other physicists I know who didn't have that kind of background or that kind of stimulus at the beginning.
So growing up, you approached science with this mindset of curiosity as you continued on in your journey.
Yes, absolutely. I mean, curiosity is the central driving force.
During a lecture at Cardiff University, you talked about how you wish the prize should have gone to the entire team. How important is collaboration in science?
Collaboration in science is tremendously important, not in all areas of science, not on all projects, but for something like the discovery of gravitational waves, uh, which was what we got the prize for, Ray Weiss, Barry Barish, and I. It could only be done by a large collaboration because it was such a complex challenge to build these gravitational wave detectors. And my view, the purpose of the Nobel Prize, I think it's pretty universally agreed by the people who award it as well as the recipients, is to inspire people about science. And the attitude that the Nobel Committee takes is that individuals are much more clear icons for science than a large team would be. And so they want to give the prize to individuals for that reason. On the other hand, it seems to me they also have an obligation to teach the world about science, how science is done, and inspire the world about what kind of science is going to really be effective in solving the world's problems. And a large portion of that science that's crucial for solving the world's problems is collaborative science. So I have had very strong discussions with the members of the Nobel Committee, the foundation, about the fact that they really have an obligation to educate the world about collaborations because collaborations are so important. And the ideal way to do it is to give prizes occasionally to large collaborations to highlight the importance of collaboration. They're not doing that, and I think they're doing a disservice to the world.
Why are concepts that students are learning in physics, such as Doppler shifts and Newton's laws? I think a lot of students take those classes and study those topics and they sort of feel, this is fundamental stuff that I need to do to pass the course. But why is this so important, and why is this so important specifically to the type of work that you do?
Well, it's important to the type of work I do, of course, because these things underpin the kinds of science and technology that I'm involved with. But I think the bigger issue is that it's not just people who are going to become scientists like me, but people who are not going to become scientists, but are citizens of the world, who, if they fail to have some basic sense of what science is and what it can accomplish, then and if the great majority of the population does not have that then we're in very big trouble, because science is the key to solving problems like the coronavirus pandemic, problems like global warming, problems like the control of nuclear weapons. And it's also the key to creating the technologies that will make life far, far better for the human race. And general population that is pretty ignorant of science is likely to allow very bad choices to be made. And frankly, I think that is what has happened in the Trump administration, and that is what has been so disastrous in the Trump administration, is the failure to follow the science, and the failure of a large portion of the population to insist that the science be followed, with masking, for example. A basic sense of science is really on the part of the citizenry of the world, is central to a good future for the human race.
And how do you think that students today can really emphasize the sciences? What can they do to motivate themselves in a world where sometimes it's not very clear, how valuable science is?
Well, I think the one thing that is very important is that we have teachers who inspire students to get some sense of how valuable science really is, and also how interesting it is. Partly, young people, all people need to be inspired about science, but their curiosity needs to be piqued. Um, we We're born curious. Almost all small children are very curious. We lose our curiosity, most of us, as we grow older. I think sometimes it gets beaten out of people by the educational system. But whatever happens, this loss of curiosity is really very troubling. And so I think central to this is trying to stimulate people to remain curious, but also trying to help people understand and see in real examples, in everyday examples, the beauties of science and what science can actually achieve. I'm sitting right now by the sea. I watch the waves roll in on the ocean, and it's so marvelous to see these waves row and then start to break and then froth. And why, how does that come about? That's the kind of thing that people should be stimulated to be curious about, and they should be given some answers at a level that is fairly easy to grasp. But that's very much of what is needed.